Right, I take that as a no. More on that in a bit. Let me begin with a word of prayer. So, Dear Father, we thank you for this day. Again, I thank you for this class and this opportunity we just have to meet and study your creation together. Help us to glorify you, what we do, and understand a little bit more about linear algebra, Lord. In your name I pray, Lord Jesus. Amen. So, I guess I will tell you a little something about your homework. And so, like, one of the questions is about calculating the intersection of two subspaces. And like, as a general rule of thumb, it's way easier to think about intersections in terms of equations. Thinking about intersections in terms of spans, it's kind of a pain. So if you can convert a span to an equation, well, that's sometimes helpful for intersection questions. So that's just like a calculational trick that I'm fond of. So let me show you how that goes. So suppose, so this is just kind of a calculational side adventure here. But suppose you had W is like the span of, I don't know, let's say 1 plus x. We'll keep it relatively simple, all right? And that's a subspace of, let's say, P2R. All right, so I've described it as a span, right? How can we describe this as an equation? So here's what I would do. I would say ax squared plus bx plus c in W. What's that mean? That means that ax squared plus bx plus c is equal to like c1 times 1 plus x, right? Tell you what, let me make this a little bit more exciting. Instead of just doing a one-dimensional span, let's bump it up a notch. So let's throw in x squared, okay? Does that make sense? You guys got me? So I threw in x squared. So we don't just have c1 times 1 plus x. What else could be in here? Like c2 times x squared, right? So the game I'm playing right now is I'm searching for equations involving a, b, and c which describe the object. So how do I do that? Well, pretty simple. Look at x squared. On the left-hand side, I've got a. On the right-hand side, I've got what? C2. All right. Look at x. What do I got? On the left-hand side, I got b. On the right-hand side, I've got C1. Okay, great. Look at 1. I've got c equals to what? C1. All right. So you want to take these equations and you want to eliminate the spanning variables. In this case, C1 and C2. Right? And so we don't really, I mean, you can do highfalutin linear algebra to figure that out, or you can just kind of like use common sense. Okay, so apparently B equals C, and well, A is free. Right? I mean, A is, sometimes you can't eliminate it if one of the variables is actually free. So A is actually free here. See, there's no equation intertwining A with B and C, right? Okay, so then W has the form ax squared plus bx plus c such that, well, b is equal to c and a is a real number. And if you undo what I just did, let's see what happens. So I've got b equals c.
Do we have to constrain b and c to reals as well?
Yeah, fair enough. Yep. So I've got ax squared plus bx plus b, such that a and b are real numbers, like you told me, right? And then what? Well, I mean, what is that? That's a times x squared plus b times what? So look, the circle's complete, right? So this is the span of x squared and x plus 1. Of course, we already knew that, but there you go. So if you want to convert from a span to an equation, you can do it what you want to do is take an arbitrary element of your space and, like I did right here, try to like eliminate as much as you can the spanning variables in place of the parameters of the arbitrary object. So if this is W1, let's say, and suppose W2 was equal to, I don't know, like f of x in P2 over the reals such that, let's say, f of minus 2 equal to 0. Well, what this means by the factor theorem is that that can be written as x plus 2 times, well, ax plus b. By the factor theorem. So apparently, we have ourselves the situation a times x squared plus 2x plus b times x plus 2. Right. So what's the spanning set here? There you go. That's a basis for W2. If I wanted to, yeah?
Would you be able to factor, you could be able to factor that further, right?
Well,
Because, I mean, you take an x out of the...
yeah, I know, but I tend to write them in standard form. But I wouldn't take points off if you wrote it like this. Like that's okay. You could do that.
Could you not then take the factor x plus 2 out of that whole equation? Would that mess with stuff?
So you want to. So what you're saying is that x times x plus 2 and x plus 2 are related. Like one is a multiple of the other. Is that what's bothering you?
Well, I mean, I'm saying if you take the whole sum of a times quantity x squared plus 2x plus b times quantity x plus 2, if you factored out the x from the x squared plus 2x, then you could factor out from the whole.
Oh, we mean go back up.
You could factor out.
Like up here? Like, I mean, that's where we started, but.
I'm just saying, if you go to the next step, factor out an x, then you have an x plus 2 factor in both of your terms. Then could you factor that out and do something with that?
Yeah, then you factor the x plus 2 times ax plus b, which is what we came
So
from.
the reason,
Oh,
I mean,
did I just miss a step?
maybe, but
Okay.
like you might, I mean, here's a temptation I had as a student at this point. It's like, well, these are linearly dependent. One's a multiple of the other. What kind of multiples are we allowed? When we talk about a vector being a multiple of another, let's think about that. It's with respect to the scalars where? In the field. Is x in the field? It is not. X is a function. Or if you like, it's an indeterminate. It's a monomial. It's not in the field. So that wouldn't count. This doesn't count as a scalar multiple of that. You can prove that x times x plus 2 and x plus 2 are linearly independent. Suppose one is a multiple of the other, right? If they're both multiples of each other, you can divide by x plus 2, and it would give you basically k is equal to x, which is saying that the constant, the multiple is equal to x, where x is where the multiple is a constant and the x is not a constant. That's absurd. You can't have that, right? So like, if I say that one of these is a multiple of the other, it leads me to an absurdity. So these are definitely not linearly dependent. Alternatively, you could put a constant times this plus a constant times that equal to 0, and you could prove by like equating coefficients of the usual stuff, usual monomial basis, that those constants both have to be 0, therefore that's linearly independent. For two things, I like the multiple argument sometimes. It's just clean. Because it's usually easy enough to see by looking at it that that's true, right? And if you write a sentence on your solution that says, these are linearly independent because the first vector is clearly not a multiple of the second vector, a professor would have to be a real jerk to not give you credit for that, right? You're like, so you might be like, well, that doesn't really make me feel better because you're teaching, but you monsters. Let's see here. So, and Anyway, so that's just some helpful hints on whatever problem that was. We're talking about intersections of subspaces. So like some other things, like I really didn't get to the intersection thing yet, but if I was thinking about W1 intersect W2 here, right? I would be looking for ax squared plus bx plus c such that what conditions hold? The condition for W1 and the condition for W2, right? So the condition for W2 is just that f of minus 2 is 0, right? Which is that 4a minus 2b plus c is equal to 0. That's from W2, right? What's the condition from W1? Well, if you take the spanning perspective, who knows? It's complicated, right? But if you do what I did, well, it is actually, what's the condition for it? It's b equals c, right? There is no condition on A, so you don't have to count for that. So where both of those conditions hold is the intersection, right? So all you do is, well, this one's pretty obvious how to solve it, right? We just put b equals to c up here, where we get 4a minus b equal to 0. So therefore b is equal to 4a. And of course b is still equal to c, right? So that tells me that my ax squared plus bx plus c actually equals what? I can put everything in terms of a, right? I've got a x squared plus 4ax plus 4a. In other words, I've got a times x squared plus 4x plus 4. If I didn't miscalculate it, that's what's in the intersection of these two subspaces. If I'm right, that thing I just wrote should satisfy the conditions for both subspaces, right? So it has b equals to c, and it has a equals to whatever. Okay, fine. So it satisfies this condition. And what happens when you plug in minus 2? Plug in minus 2 into this, we get what? 4 minus 8 plus 4, also known as 0. So these two subspaces intersect in a one-dimensional set with basis x squared plus 4x plus 4. So there's an ABC part problem where I have things about intersection of subspaces. I just wanted to give you guys some like calculational help. And so anyway, there you go. Now if you haven't looked at it yet, then oh well, I'm sorry. That would not be the best way to do this class, but oh well. All right, so here is the attendance sheet. Let me get back into the algebra. So we're talking about linear transformations, right? And we had gotten all the way to the proof that the linear combination of the composite of linear transformations is once more a linear transformation. The next theorem on our docket is it's hard to appreciate it given your current like education, but as you go on in math and you understand other contexts, this is actually a very surprising theorem in some sense. So here it is. Suppose T, a linear transformation from V to W, has inverse function S from W to V. Then S is an element of the linear maps from, I seem to have, I think I was using a script L before, right? I'm sorry, I seem to be, I can't make up my, oops, it goes from W to V, right? So, yeah, sorry, I stylistically inconsistent. If you'd like, I could invent a third notation that's popular in other places. Some people just call HOM. T is an element of homomorphisms over the field VW. Like, this is a more abstract algebraic notation that's sometimes used. All right, so let me try to unpack what this theorem is saying. It's saying that if a linear transformation has an inverse function, it's automatically the case that that inverse function has to itself be linear. All right? So here's the proof. So we're given that T composed with S is equal to the identity on W. And we're also given that S composed with T is the identity on V. That's what it means for S to be the inverse, right? Its composition in both directions gives you the identity either on the domain or the range here. So let C be in the field, and let's say X comma Y be in W. Then note, if we look at S of Cx plus Y, right? We're trying to show S is linear. We need to show that we can pull out constants and that it's additive, right? Right? So how can I change X? Now so I can do what? I can say, well, that's really S of C times T composed with S, right? Of X plus T composed with S of Y. Do you guys understand why I can do that? X and Y are elements of W. I mean, I should put Cx in there, my bad. I got to do for Cx, not for X alone. All right? I can do that because remember that T composed with S is the identity on W, right? What does that mean? Identity on W is such that like id W of X is equal to X, right? Id W of Y is Y. So that's just an identity. What's the definition of composition? Right? What can we do now? What do we know? What data do we have to work with in this proof? Yeah?
We know that. Oh. Wait, never mind.
I mean, I didn't write it in the black part, but I wrote it in the blue part, as is my custom in class. I don't always rewrite everything in the proof itself. Sorry about that. But that is kind of like common math parlance. Like if you read articles and stuff, a lot of time proofs won't restate conditions that are made in the theorem. It's understood that you're looking at those, conditions. We're assuming T is linear, right? So that means that I can take this and that, and I can rewrite this as just S of T of, S of Cx plus S of Y. Right? By linearity of T. So this is, since T composed with S is the identity in W, this is definition of composition, and this right here is by linearity of T. And then now what? What are we looking at? We're looking at S composed with T of something, right? But S composed with T is the identity, right? So S composed with T, they cancel, and you're just left with S of Cx plus S of Y. And I feel like I have messed up my proof, right? Because what did I want? I wanted to pull that C out, didn't I? So what mistake did I make? What should I have done? what do I have the freedom to undo? See here, I put Cx in here, right? I should have just left it out. I should have just left C out here. If I'd done that, see, like this, all the steps still legitimate, and that puts, you know, that would, well, right here, I would bring the C inside by the linearity, right? And then that puts the C outside here, which is where I want it. Thus, S is an element of the linear transformations from W to V. This is nice because if you can somehow or another prove a linear transformation is invertible, that it's what's called a bijection, you don't need to check that the inverse is also linear. It's automatic because of this theorem. The inverse of a linear map is necessarily linear. This is not true in other contexts. Like, for example, if you have a continuous map, which is invertible, it does not have to be the case that the inverse of a continuous map is itself continuous. All right? Maps that are actually like that are called homeomorphisms. They're a special kind of map when we study topology. Anyway, there's that. So there's one. The next two theorems are also particularly nice. So theorem 3.1.26. Here we have T and injective linear transformation then S linearly independent implies that T of S is linearly independent. So that's one thing. And the other thing I can tell you is that if L is linear and U is linearly independent, then the inverse image of U under L is linearly independent. So the forward image, we need a condition on the linear transformation to preserve independence. But the inverse image is different, right? So, like, can you guys see why one has to have conditions? How about this? What if you've got the trivial transformation, right? Just everything maps to 0. Feed that a linearly independent set. What happens? It sends it to the 0 set, which is linearly dependent, right? So we need some kind of condition to preserve linear independence. So let's prove these. So number one, assume T is 1 to 1 and S is linearly independent. Let, let's say T of x1, T of x2, T of xn be elements of T of S. All right, so take a finite collection of points in the image under S, right? What does this suppose? So here, I mean, which implicits what? x1, x2, xn are where? These are necessarily, well, in the vector space, yeah, this is all inside of a vector space, that's true. But here, they're in the image of S, right? So if I'm talking about these being in T of S, what I mean then is, of course, that these x's are where? They're in S, right? I'm trying to prove at the moment the linear independence of the image of T, of S under T. So what do I have to do? You're like, you put them in a determinant and you calculate the determinant, and if it's non-zero, they're linearly independent. We can't do that though. These aren't column vectors.
Different constant terms and set them equal to 0.
So, okay, so you're saying take a linear combination of these guys. Like this, and set it equal to 0. I agree. T is what?
Injective.
It's injective, but it's also more, before that, it's linear, right? So, remember we learned the linear combination of linear combination is, ooh, wonder what that's about. I gotta be careful, that might be a copyright strike. I know. I'm still waiting to see if I get demonetized from that word I said the other day.
Wait, what?
No, I said a word that YouTube doesn't censor. Not YouTube, I mean Yahoo doesn't censor, Yahoo comments. I mean, they censored it, but they said they don't censor words, so they must not censor the word that they censored. It's all very confusing to me, but I don't really understand community guidelines, so what can I tell you? So this is equal to 0. Now you told me that t is 1 to 1, that's true, and we proved last time that if t is 1 to 1, its kernel must be 0. But this right here is in the kernel of t, which by the way is 0. We're going to write 0 without the set here. I hope that's okay sometimes. But technically speaking, it's the set containing 0. If it's, I've already spent this much time talking about it, they're better. But okay, technically it's that. So then what? C1x1 plus da, 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 plus cnxn equal to 0, which tells me what? Well, these are in S, right? S is linearly independent. What does that tell me about this linear combination? What do the constants have to be equal to? 0, right? So C1 equal to 0, Cn equals to 0 by linear independence of S, right? But what have I just shown? I've shown that if we take a linear combination of elements in the image, it forces it to be the trivial combination. It forces all the coefficients to be 0. Therefore, T of S is linearly independent as claimed. I'm asserting in 2 that we don't even need any condition on the linear transformation whatsoever. Like, it's enough for it just to be the inverse image of a linearly independent set. Right? So let me look at the proof of that. If I'm not, well, let me check on time. I did spend some time working on your homework at start of class. I may be further along, and yeah, I think I'm going to have to leave the proof of the other part there. Well, wait a minute. No, we got time. I forgot. We got 5 minutes afterwards, and since I started 5 minutes late, we have till 4:10, right? No. You say you have all day?
Yeah.
All right. You have a dynamics. You say you have a final? Wait, what? All right. Sorry, I'll behave. That's not true. So anyway, so here's the other part of it. Let u equal to u1, u2, uk. Be linearly independent in W, and L an element of the linear maps from V to W. All right. Suppose we have x1 through, where I lost my place, x1 through xn in the inverse image of u. All right? And we'd like to show it's linearly independent, right? So suppose what? Suppose c1x1 plus c2x2 plus cnxn equal to 0. what happens if we hit the equation, hit this with L, right? This gives me L equals L of 0, which is 0, right? But what else is it? By linearity of L, this gives me what? C1 L of x1, Cn L of xn equal to 0. What does that mean? What does that tell me? Wait a minute. But notice that L of x sub I are an element of U, right? Since x sub I is an element of L inverse of U by assumption. That's what this means. If x is in the inverse image of U, that means when I feed this to L, it goes to U. Therefore, these are all in U, which we assumed was linearly independent. Therefore, the coefficients are all 0. Which implies then that, L inverse of U is linearly independent, which is what we're out to prove. So there's that. It's funny that you don't need any condition. You don't need any condition at all for this, right? Just linearity is enough. The other way, we did need to know that the only thing that maps to 0 is 0. That was the difference, right? Okay, so the next theorem, 3.1.27, is concerning spans. And so here it is. T from V to W, all right, is surjective if this is surjective linear map, then if the span of S is equal to V, then the span of T of S is equal to a W. So surjective linear maps map spanning sets to spanning sets. If you put in a generating set, you get out a generating set if your map's a surjection. And I won't go through the proof of this one. It's actually easier than the ones I just went through. So guys, that brings us back now to a simpler time. 221. Now we are going to talk about standard matrices. So this should be your happy place, yeah? All right. But I'll find a way to make it weird. I'm just joking. I hope that I'll find a way to convince you that we can prove things about standard matrices pretty easily if we adopt the right notational scheme. And so the starting point is the fundamental theorem of linear algebra, which I don't know if you knew this is the fundamental theorem of linear algebra, but I'm just a little bit joking. There doesn't really seem to be agreement on what the fundamental theorem of linear algebra is. But I owned a linear algebra book once that called this the fundamental theorem of linear algebra. And it's the first place I heard it, so it stuck. But here it is. L, a mapping from N to M column vectors, is linear transformation if and only if there exists A in the M by N matrices such that L of x is equal to AX for all x in Fn. All right. So, I mean, we do have some notation for this that I will use on occasion, especially like about 2 lectures from now. I should just mention this. Like, in this situation, I say L is equal to L sub A is notation for this. All right. In other words, L is left multiplication by the matrix A. That's what L sub A means. All right. If you like, I could switch from L to like T here to make it look different. So this is an if and only if proof, right? So that's a biconditional. We have to prove both ways, right? So let's go this way. So we've got L linear, right? Let x, which of course is what? The sum I equals 1 to n of x sub I e sub I be an element of Fn. Then L of x is equal to the sum I equals 1 to n of x sub I L of e sub I, using by the linearity of L. Yeah? By linearity of L. If I repeat it, it makes it more true. By 3 times, I'm preaching. All right? So there you go. What does this have to do with matrix multiplication? Well, what is that? I'll write it out this way. That's x1, L of e1, x2, L of e2, which is the matrix L of e1, L of, that was an n. I'm a dummy. Sorry, but you knew that already. x1, xn. So that is the matrix. What is the matrix? It's this. Right? And of course we have a name for that, right? That is the standard matrix of L, right? So our notation for this typically is standard matrix of L. So that's the forward implication. How about the reverse implication? The reverse implication is easier, right? Suppose L of x equals to ax, right? Then if we have L of cx plus y, we have a times cx plus y, which is cax plus ay, which is c times L of x plus L of y. Therefore, L is an element of the linear transformations from Fn to Fm. N as in nanu nanu, and M as in mummy. There you go. Proved. Not much of a fundamental theorem, really. Ah, I was robbed. Any questions? Comments? Concerns? Like, can we please have like a couple of these on the test, right? Like find the standard matrix, right? It's not bad. So we've talked about linear transformations being one-to-one, linear transformations being onto. How does that square with the standard matrix? What's the theorem there? When is a linear transformation one-to-one? What do you need? You need the kernel to be 0, right? What is the kernel as it relates to the standard matrix? The null space, that's right. So notice that the kernel of L in this context would be, x in Fn such that the standard matrix of L times X is equal to 0, right? But that's exactly the null space of the standard matrix of the linear transformation. And the range of L, or if you like, the image of L would be what? That is AX such that X is an input, right? But what is A times X? It's on the middle board right now, right? A times X is a linear combination of the columns forming the matrix, right? This is nothing more than an elegant notation for a linear combination of the columns of A where the weights are taken from the components of X. This is the span of the columns of A, right? The span of the columns of A is what we call column space. So null space gives you the kernel, column space gives you the range or the image, right? So when is the map, when is the linear transformation 1-to-1? Well, you need the null space to be 0, right? When is a linear map onto? You need the column space to be as big as, FM, right? In other words, you need for it to be well, yeah, I mean, we could say more, but I have, so like if you read theorem 3.132, 1-to-1 if the columns are linearly independent, it's onto if the columns span FM, right? That's a close cousin to what I'm saying here. What else can we say about standard matrices before we leave this? Because we'd like to just review, like, how do standard matrices work if we take like a linear combination. It's like about Angry Birds. I was about to say that word again. Have to be careful. So what's the standard matrix of the sum of two transformations? Right, so let's let T and S be linear transformations of column vectors for a second here, yeah? So how does this work? If we look at, EI, that's what? It's like T plus S of E1, dot, 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 T plus S of En, right? Which is T of E1 plus S of E1, T of En plus S of En, right? Which we can rewrite as T of E1, T of En, plus the matrix concatenated by S of E1, S of En, which is the standard matrix of T times EI plus the standard matrix of, oh, I'm an idiot. Well, this can be easily fixed. I'm sorry, I got carried away here. Help me fix this. How do I fix this? It's very easy. Next up, we'll do T composed with S of EI. And this time I'll actually do that. This time I didn't, right? I didn't do this. What'd I do? I just wrote out the full thing, So I completely undid the goodness of what I was trying to do, which was to not write all this, to write it instead of here I've written all n columns. I was trying to just do it for the ith one, right? I failed. Sorry. Let's try it for this one. So here we have T of S of EI, right? But anyway, this does prove that the standard matrix of a sum is the sum of the standard matrices. Hooray. This one, check this out. So how does that work? Well, this is the standard matrix of T times S of EI, right? But by definition of standard matrix in the theorem, the fundamental theorem of linear algebra, that's the standard matrix of S times the standard matrix of T like this times EI, right? But this is also equal to the standard matrix of the composite times EI, right? By the fundamental theorem of linear algebra. But what are both of these? What's the left-hand side and the right-hand side? What's the significance of both of these? What are they? Remember, what does it mean if I take, just let me take T and S out of the picture. If I take B times EJ, what's that equal to? That is equal to column J of what? Of B, right? So what are you looking at? This is the ith column of the standard matrix of T composed with S, right? And this over here is the ith column of what? The product of the standard matrix of T and the standard matrix of S. So you've got you have many different ways to prove equality of two matrices. I don't know if you thought about this or not. I've been telling you guys a lot on, we can prove that the ij component of both are equal, right? Match up arbitrary components, index level calculation. You can also do column level calculation, column vector level calculation. This calculation shows that the ith column of the standard matrix of the composite is equal to the ith column of the product of the standard matrices. If that's true for every column, it follows we have matrix equality, right? Can you guys think of other ways you could prove two matrices were equal? What if you could show every row matches? That would do it, right? Or how about if you could show every rectangular, like a square subset starting at the lower diagonal, right? Like if you could show that this part matched, then this part matched, then that part matched, and then that part matched. Like if you could do that over the whole thing, right? If that partitioning fits out the whole matrix, if you can show that it's equal across both and it covers all components, then that would show equality, right? There's so many other ways to prove equality of matrices that we haven't really talked about. But oftentimes, just column equality or component equality is what I use. Now, I used to teach this using components, and it's much, much slower. I then sat in on a class by a professor who used to teach linear algebra here, and he did things with columns, and I was like, oh, I'm doing it wrong, you know? There's a deeper truth here, which is maybe something you haven't thought about, which is why do we define matrix multiplication as we do? It's actually so that this happens. Defining matrix multiplication as we do makes the matrix of the composite the product of the linear transformations composed. That is by design. We want that to happen, all right? So next time, we'll talk about the problem of taking a linear transformation and extending it or restricting it. And we'll start to talk much more intently about what is it we call, if you have a linear transformation, which is also one-to-one and onto, this have a special name. They're called isomorphisms. So basically, two vector spaces which are isomorphic, they're the same vector space in some sense with a different notation. We've already been working with one isomorphism in here. Do you guys know what it is? What linear transformations are bijective that are all around us and they're full of your homework right now?
Polynomial space?
Polynomial space? No, I mean maybe, but I mean you could find an isomorphism from polynomial space to some other space, whatever, but coordinate maps. Coordinate maps are linear and they're one-to-one and they're onto. So like a coordinate map is an isomorphism from a finite dimensional vector space to column vectors. And that's why they're so useful. Because in the world of column vectors, we can do all this stuff, right? And we have all of 221 at our disposal. So anyway, I will help you guys with homework if you come ask me about it. But you got to ask me about it. Thanks, guys. Oh.